All right, let's talk about equations of lines. But kicker's going to be in 3 dimensions. We're going to have lines that go off into space instead of in our 2 dimensions. Now, if we think about 2 dimensions, first of all, what do we need for lines in 2 dimensions? The xy plane. But what information do we need to do a line in 2 dimensions? We need two points using the independent and dependent variable x and y. You need 2 points. But if you boil it down to when we put it into the equation, y equals mx plus b, let's say, you need a point and its slope. Because when you do the 2 points, you get the slope between them, and then you use that slope. So a point and a slope. Well, if you think about slope, what that's telling you is it's telling you direction. And that's where I want to go with this. That is, equations of lines in 3 dimensions, you need a point and a direction. Yeah. Now, in 3 dimensions, our direction comes in the form of a vector, because if we have a vector, we know which direction it's going. I mean, that vector can move around. And so basically, what you need for an equation in 3 dimensions. So you got x, y, and z here. So we need that point out in space, wherever it is. And then you need to know the direction of it, whatever it's going. And so that way, you've got your line. Okay? So you need this point x, y, z. And I think they usually call the direction vector v in this book. Let me make sure on that. R. Well, no, v. They do call it v. Okay. All right. Okay, and so here is what now. Usually the way they give v, though, is they'll give v in the standard form from the origin, directed from the origin. V is some direction to the vector, the ABC, is what they're calling it in this section. And so this v, which of course we can translate that wherever you want to. Vectors don't really care where they are, but they do give us the direction. Okay? All right, now, this line is parallel to that point. And now, the actual point here that they give us, let's just call that x0, y0, z0 is the usual designation that we'll make on that. All right, so we want a line through x0, y0, z0, and make it parallel to this v vector ABC. So got a vector like that, so that's going to make our line wherever we want it. Okay? All right. So to kind of build our way up here, let's do it a couple ways. You know, the ultimate goal is to be able to get points on, well, the equation is what we're looking for. But the way we're going to do it in 3 dimensions is we're going to do it by, and I guess this is the way we do it in 2 dimensions. We just don't think of it this way. We're going to do it by giving the x, y, and z values of each point on that line, or be able to come up with the x, y, and z, which if you think about it, that's the way we do it in 2 dimensions. We get the x, y equation, so we can get the x and y points, all the x and y points on that line. Well, it's the same thing in 3 dimensions. We're going to define the line, the equation of the line, using the x, y, and z, the values of x, y, and z for each point. So we're going to come up with some way to get every x, y, and z point on that line. Okay? So here's how we do that. First of all, let's we're going to have this parallel vector from the original point that's given to all these other x, y, z points. We're going to define that vector as u, vector u. And what would be our u vector then? How could we define that? Well, from point to point, what do we do to define the vector? Subtract. Yeah, we subtract the components. So you go x minus x0, y minus y0, and z minus z0. Okay? All right, now, what is true then about the vector u and the vector v? They're parallel. They're not necessarily the same length, because in vectors you've got direction, magnitude, length, and the direction, so to speak. So they're not the same magnitude, but to be parallel here, they have to be multiples of one another, right? This one would have to be a multiple of this one, or vice versa. You know. And so let's just call that multiple t. So u, we can say, is some multiple of vector v. Okay? All right, well, what this does is this sets up a little equation here. U is this, the difference of the components here. And then the other side is then some multiple t. T is just a scalar. So we multiply that by vector v, which is the ABC, they're calling it. So what that does is then that sets up an equality amongst the components, right? We know that x minus x0 would have to equal what over here? TA. The y minus y0 would have to equal the TB. And then z minus z0 would have to equal TC. Solve those for x, y, and z. Solve that for x, you get x equals x0 plus TA. Y equals y0 plus TB. And then z equals z0 plus TC. This right here then describes our line, because that gives us each x, y, and z on the line. So this is called, the book calls this one the parametric equation. Of the line through x0, y0, z0, parallel to vector v, ABC, components ABC. Okay? All right, so that's our parametric equation form of a line in three-dimensional space. And so it's really, if you've got those two things, that's really an easy thing to do, right? All right, so let's find the okay. So why would they phrase this parametric equation? Why would they call it? Because it's going to vary based on the value of t, right? T equals 1, then you get just like we've worked with parametric equations before, similar to that. All right, so let's find the parametric equation for through 2, 3, 1. It's parallel to the vector -1, 6, and 5. And the parametric equation through 2, 3, 1 that is parallel to 1, 6, 5 vector. Well, it's just a matter of writing those down. X is x0 plus t times a. So this is x0, y0, z0, the point we're going through. And this is a, b, c. So x is x0 plus ta. So that would be 2 minus t, or 2 minus t times -1, right? Which is 2 minus t. The y would be y0 plus tb. So y0 is 3 plus 6t. And then z is z0 plus tc. 1 plus 5t. So that would be our parametric equation. So what this gives you, I mean, it doesn't give you a nice little equation, I guess, but it does give you a way to find the x, y, z. So if I wanted to find 2 points, 2 other points on this line, how would I do that? Yeah, we could do t equals 1, and that would give us an x, y, z, right? If t equals 1, we'd have 1, 9, 6. And if we did another t value, t equals 2, we would get 0, 3, 15, yeah, 15. And then 11. Okay. And so, we could build our line that way. So anyway, just a different way of kind of thinking of it. Now, here's another way that we can think about building a line. It comes out fairly similarly here. They'll also ask for this form of line, but we can get it different ways. All right, so let's say we've got, here's x, y, and z again. So here's our point, x0, y0, z0. And we want it parallel to this vector v. Well, the other way of kind of thinking about the hold on just a second. All right. So we want trying to find a different way here of thinking about an equation, building it up a little differently. Let's let R0 be that vector from the origin to the x0, y0. And so R0 would be designated vector-wise x0, y0, z0, right? That would be the vector form of that, right? Because you're just subtracting x0 minus 0, so forth. All right. Now, R then, let's say we've come, so our line's parallel to this v vector. So let's come out to, x, y, z, any point on that line. And let's make R be that vector. So R would be x, y, z. Just in component form, right? Okay? So, if we use a little addition of huh? I did, but it switched around on me a little bit. All right. So we did R0 is the vector from the origin to the x0, y0, z0 point. And then we did vector R is from the origin to any point randomly picked on that line, x, y, z. Well, with a little vector addition here, do we not see that my this R would be the addition of this vector plus this vector? R0, so R would be the addition of R0 plus this vector. Now, that vector, we know the direction of it, same as V. However, does it have to be the same magnitude as V? No, it's some other, a multiple of V, right? Yes. So R is the vector R0 plus t times the original direction vector we were given. Okay. So this is just another way to kind of think of it. This is what they call the vector equation of a line in 3 dimensions. It really is the same thing, turns out, because R0, that's the vector from your original point, and then t times v, that's a scalar multiple of v. So, let's see. So let's see what the vector equation for that same line. The line through, I believe I did 2, 3, 1, and parallel to the vector -1, 6, 5. Okay, so the vector equation for that would be this R vector equation, R0 plus t times v vector. All right, so from that, R0 vector would be just 2, 3, 1. Just turn it into a vector. So R would be the 2, 3, 1 plus t times the v vector. Well, this is the v right here, right? -1, 6, 5. So what does R, that vector, look like? but you're just adding components, right? So it'd be 2 minus t, 3 plus 6t, and then 1 plus 5t. Does that look familiar? Isn't that x, y, and z from the parametric? It's the same thing. It's the very same thing. I'm not sure, but we could write that using the ijk vectors. The book, I think the book 2 minus ti, just to remind you there, plus 3 plus 6t j plus 1 plus 5t k. Okay. All saying the same thing. It's just that now the line, this line is really by where the tip of the arrow points. You know, that's how we're going to generate this line if you put it in this format. But it's going to be the same because remember the equation of this line in parametric form was x equals 2 minus t, y equals 3 plus 6t, z equals 1 plus 5t. So they're very similar. Now, okay, I'll make that point here in a second. Okay, so far so good.